Hello and welcome back to another lecture from organic chemistry. In last lecture, we reviewed the case that what will happen if we start with cyclic diene molecule and react it with an dienophile that it has two functional groups, and then both of them happen to be electron withdrawing group. And in that case, we have a possibility of getting two different products. One is endo and the second exo. Endo has two functional group or electron withdrawing group that close to the double bond, and exo are far from the double bond. As you see, the endo is the major, while in the exo it will be the minor product. The reason for it was like in the transition state, whenever the functional groups are in an endo position, they can have a pi interaction, or they can have some interaction with the new pi bond, and that's going to drop the activation energy, and it will favor the transition state, so the reaction will be faster. So technically, we have the right to say the endo products are like the endo product are favored by kinetic, while the thermodynamics says that the exo is the most stable product. And again, the reason for it, I said endo has lower activation energy, so kinetic is going to favor it. But when we look to the final product, exo is more stable than the endo. That means exo is going to release more energy, so the system will be more stable at the end. Now, what will happen if we take a symmetrical and diene and react it with dienophile? In that case, we have only one option, so we get only one product, and nothing is surprising here. But if we take an unsymmetrical dienophile and react it with let's say, if we take a non-symmetrical diene and reacted with dienophile that it has functional group, in that case we have two possibilities. Maybe both functional groups are on the same side, or maybe they are trans or far from each other. Okay, let's review both cases. So one possibility is to establish interaction between here carbon number 1 and one of the carbon on the dienophile, and also carbon number 4 with the pi bond of the dienophile. So we will get such a product. We get a ring, and so the double bond is going to move here. This one is going to move there, and the dienophile, the double bond, will move between carbon number 1 and one of the carbon and dienophile to establish a sigma bond. Now we'll have a double bond here, and then MEO there, and aldehyde is here. Okay. Next one is we can have the same traction, similar to the first reaction I wrote, but this time I just simply rotate the molecule, look to the position of the like a position of the aldehyde. I just really moved it down. And maybe instead of saying, like rotating, I can say that, I just first I flip the molecule and then rotate it. And it's possible. All the time, the molecule is spinning around itself, and like it can flip, and that's 100% fine. Okay. Now, if we establish interaction between them, we will get similar, molecule. Only difference between them, between number 1 and number 2, is going to be position of the functional group. And in this case, the aldehyde. Okay. Let's label the double bond and aldehyde. Okay. So from anyone, like you start labeling, you can see that the methyl group, the methoxide group, and then in the first molecule is just technically 1, maybe 2 carbons. I can say 2 carbons. If we start from, for example, this one, and then on the second one, we're going to see the aldehyde group, and then for the second molecule, any way you move 1, 2, on the third carbon, we're going to see the functional group or the aldehyde. So these two molecules are really not identical. They are isomers. They are constitutional isomers. So I'm going to say these two are not identical and non-identical molecule, but they are isomers because they have the same formula. And in this case, we say they are regioisomer. And what's a regioisomer? Regioisomers have the same connectivity. But when it comes to functional group, the position of the functional groups are different, okay? Position of functional groups are different. So in that case, we say we are dealing with regioisomers. Okay, now which one of them is more stable? Again, let's review the chemical reaction that we're talking about. We have oxygen with a lone pair. Oxygen, it can share this lone pair, and then that double bond is going to move there. So what do we get? We will have a double bond here and maybe a negative charge there. Negative charge on this oxygen. Okay, of course, we're going to have a positive charge on oxygen. How about the aldehyde? Aldehyde, okay, the dienophile. Dienophile, it can share the double bond here and let oxygen to take, the pi bond or the double bond. So we will have a new lone pair on oxygen, and there will be a positive charge on this carbon. Now, I want you to highlight position of the charges. As you see, they are facing to each other. So there will be a driving force to bring these two close to each other, and that's going to speed actually the reaction. Now, how about the second one? The second one, and again, I'm going to repeat the same thing. So I'm going to say this one will move here, that one there, and like double bond is going to move here, and this one will give new lone pair to oxygen. So again, double bond here, negative charge there. This one will, okay. And this one is going to leave me with, okay, let's see. I think, forgive me, the position of this one is a bit like I wrote it opposite, so should be here, in fact. Okay, so what do I get here? I get oxygen with 3 lone pairs, and now I'm going to have double bond here, and that's going to leave me with a positive charge on oxygen on carbon. Now, as you see, positive and negative charges are not close to each other, and so the first attraction is going to be more favored than the second one, and so I'm going to say the top chemical reaction is going to be faster than the second one, and that's going to give me this product. Let's draw the final product. So I get a methoxide group here, double bond there, and the aldehyde it will be down there. While this one is going to give me methoxide here, double bond is there, and CHO is going to be there. So which one of them is going to be the major product? This one is going to be the major, and this one it will be the minor product. And again, what's the reason behind it? As you see, like resonance structures are favoring the top interaction because the negative and positive charges are going to be close to each other. And so this is going to happen. Okay, we will put technically electron there, and now we can have a ring, and now we can establish a ring, and that's going to actually at the end is going to give us a cyclic molecule. Remember, this one it can move back, and then we can have this interaction. Now I want to start a new subject, and it's going to be symmetry of the HOMO and LOMO orbital during Diels alder reactions. Remember that the HOMO and LOMO orbitals are the one that's going to actually interact and give us sigma or pi bonds. And so I'm going to look to symmetry of those and see whether they are constructive or destructive. And the highest occupied orbital on the diene is going to be the second orbital, and as you see, it has 1 node. Let's show the node. That's a node. A node is the place that is going to change sign of the phases. And the diene is going to put electron inside the empty orbital, the lowest unoccupied orbital on the dienophile. So HOMO from diene, it will react with the LOMO, lowest unoccupied orbital on dienophile. And now, if the symmetries are matching symmetry of the orbital, in that case, we say the interaction will be constructive. Otherwise, we need to do something about it. And so when I look to the signs, one of them, it says red here, and another one is blue. Okay, so when I bring them close to dienophile, I need to see different signs on the the LOMO orbital of the dienophile. And when they reach each other, the red one, it can see the red on it can see the red on the dienophile, and also we have a blue one, and there is a blue one, a blue lobe on the dienophile. So in that case, I'm going to say this interaction it will be favored. Remember that they are reaching each other from the top or the bottom of the molecule. So you can say this. You can say I have dienophile. This is my dienophile, and I'm going to take the LOMO orbital. Let's draw the LOMO orbital. This is the LOMO orbital, and then I go, let's say, red here. The red, it can interact with the red orbital or red lobe on the diene, and that's going to be constructive, and it will give us sigma interaction because it's a head-to-head interaction. And now I'm going to flip this one, and in that case, I will get blue lobe pointing down while the red one is up. And the blue one is going to find the blue one, and they will establish interaction, and the interaction is going to be sigma. And remember, you started from here, 1, 2, 3, 4, 5, 6 carbon. So we're going to get a ring that it has 6 members. So I'm going to say this interaction, it will be in favor, it will be fine. But what will happen if we have, like a less number of, let's say, double bonds? And the interaction until now that we are studying is 4 plus 2. 4 stands for 2 double bonds, or 4 p orbital on the diene, and 2 stand for 2 orbitals, 2 p orbitals from the dienophile. So the thing that happened here, like we had head-to-head interaction and the p orbital, now that they're interacting head-to-head interaction, that will give us a sigma interaction. So the hybridization of those carbon will change, and technically it will switch from sp2 to sp3, because now we started to use we started to use the p orbital for sigma interaction. Okay, now let's take two like a 2p orbital and interact them with a dienophile, and I have two alkene, and like technically I have two double bonds, one in each, and when they reach each other, and a HOMO from one orbital is supposed to interact with LOMO, lowest unoccupied orbital, from the second molecule. When those two interact with each other, and we can see that like the color or the face of the frontier orbital or the LOMO and the HOMO are not matching. This interaction is constructive. It will give us sigma interaction, but the red is interacting with the blue one on the left side. So I'm going to say this one is going to be anti-bonding interaction. And there is a node technically here, and there's no way to get, like in a sigma interaction and there, or to establish a bond. So what's the solution for it? The solution for it is like, instead of using heat, okay, we used to have heat. Now we are using light, or H nu. And what we're going to do, we're going to apply energy, light, and in order to excite one electron from the HOMO to the LOMO orbital, okay? And so we have, let's say we have an alkene, and from HOMO, we took one electron, the one that is pointing down, we send it to a higher orbital, and now it's sitting there. Okay, what's the highest occupied orbital, regardless of how many electrons in it? Look to the term, it says the highest occupied molecular orbital. We don't care how many electrons are there. There is one electron there, okay? Because there is one electron there, I have the right to say this is the highest occupied molecular orbital. Now look to the like symmetry of the orbital. There is a node there, so I can draw a node here, and that node, as you see, is changing the phase of the orbitals from red. Blue is turning to blue one. Now when I take the HOMO from one molecule and react it with LOMO, the orbitals are going to be in the same phase, and so interaction will be constructive, and that's going to give us two sigma bonds. Okay, so if I want to summarize it, I will say it this way: 4 plus 2 will give us constructive interference whenever we are using heat. Okay, that's completely fine. The symmetry is matching. But if we are dealing with 2 plus 2, in order to have this other reaction, we need to apply light. And the reaction, it will be visible only and only if we are applying light. Why? Because we take it HOMO, we excite it, we turn it to, we send one electron from the HOMO, and we send it to higher orbital. And in that case, I get two orbitals that they have a single electron inside them. And this is going to be the frontier orbital, and it's going to be the one that it will run the reaction for us. Okay, keep it in your mind. 4 plus 2, heat, it will give you this other reaction. 2 plus 2, only if you're applying light. And that's going to be the end of this lecture, and thank you very much.
you.